As we all know, it's been over a year now since the COVID-19 pandemic has started, and it has affected us drastically on a worldwide scale. To help fight the spread of the virus, the World Health Organization have introduced many guidelines, including, but not limiting to, self-isolation, social distancing, avoiding indoor gatherings, and finally, the wearing of face masks. Hello, my name is Amaan, and this is my dissertation presentation on a deep learning approach to real-time face mask detection on the edge. So what's the problem? Well, despite mask regulation being put into law, many people just don't follow it. Sometimes people just forget to wear them. The issue is, it's just not scalable to enforce mask regulation without the use of some sort of automation. Take, for example, a shopping centre with thousands of people and a certain percentage of them not wearing masks. It could be cumbersome to cherry-pick individuals to remind them to wear a mask, especially if they have a valid reason not to. The problem has already been explored in past papers, where they showcase that convolutional neural networks are effective in classifying masks. However, they fail to showcase an evaluation of a real-time system with the proposed classifiers. The issue is that neural network computation is expensive, making it less accessible when deploying to low-powered systems, typically taking place on a high-powered GPU for instance. This is where my aims for this project come in. This project aims to create an effective real-time face mask detection system that is easily deployable, runs on low-powered hardware, and can run on low-cost hardware. There are three main objectives to meet these aims. They are finding an appropriate dataset to train the classifier, training an effective convolutional neural network to classify mask models, and finally creating the overall real-time detection system with the above-trained CNN classifier with the above-trained datasets. In terms of the hardware that was chosen for this project, a Raspberry Pi is used as the host device, which will receive the data via a webcam feed and output the result onto a monitor. An Intel Neural Compute Stick is then connected to the host device, which will do all the neural network computation and output the resulting classification for each frame of the video stream. Onto my results and findings. Let's begin with the mask datasets. I managed to find 4 datasets in total. 2 were authentic datasets and the other 2 were artificial datasets, where a digitally augmented image of a mask was added on top of a person's face. It was quickly found that artificial datasets have a detrimental impact in classification accuracy, where the best performing artificial dataset only achieved 56% accuracy, which is barely higher than chance. It was also found that larger the quantity of data, the higher the accuracy. This was true for both the authentic and the artificial datasets. Therefore, it was concluded that the best dataset for this project was a combination of both the authentic datasets to achieve the highest accuracy. With the optimal mask datasets found, it was time to train the convolutional neural network classifiers. For this project, 3 CNN models from the same architecture were tested: ResNet 18, ResNet 50, and ResNet 101. The only difference between them being the number of layers. After training and testing each model on PyTorch, it was concluded that the larger the size of the network, the higher the resulting accuracy. And also, the larger the size of the network, the longer it took to train. Therefore, it was concluded that ResNet 101, with its 101 convolutional layers, was the best performing CNN in terms of classification accuracy, achieving 98%. Now, with all 3 models fully trained, it was time to export them to Onyx runtime, ready to be converted to intermediate representation to allow the models to be deployed onto the Neural Compute Stick 2. When implementing the real-time detection system, 2 models had to be used. The first model had to find the location of the subject's face. Intel's provided face detection model was used for this. The second model, that we have already trained earlier, had to classify if the face was wearing a mask or not. This method of finding individual faces and running inference on each face is what allows multi-classification to take place. Here is a demonstration of the system working on a webcam stream. Here is a demonstration of the system working on a multi-classification video stream. Onto the results. The metric used to measure the effectiveness of the system is frames per second. Higher the FPS, the more effective the system. 2 tests took place, a single classification video test and a multi-classification video test. FPS of each model was recorded and a theoretical maximum was also recorded, where only the face detection model was running on its own. As you can see from the single classification results, the smaller network ResNet 18 performs the best at around 6.5 FPS, and the largest network ResNet 101 performs the worst at around 4 FPS. The multi-classification results follow the same trend. However, it's worth noting that ResNet 101 only achieved an FPS of around 1.5. This may be considered unusable for an everyday application. With these results, it can be concluded that the larger and more accurate the model, the slower it performs, and also, multi-classification has an overall negative impact to every model. Therefore, a solution is proposed that certain models are best suited for certain applications. For instance, if only single classification is the priority, pick the biggest, most accurate CNN model, ResNet 101. If multi-classification is the priority, a sacrifice of accuracy has to be made by choosing ResNet 18 to maintain a usable FPS. That pretty much concludes this project. However, there is still a lot of scope to add on or to improve this project in the future. The first improvement I can think of is adding a third classification for incorrectly worn masks. This will require an expansion to take place within the dataset to add another set of labeled data for incorrectly worn masks. Second, more CNN architectures should be explored, studying the effects they have on accuracy. Also, the use of neural network compression, quantization, and pruning. For example, would it be possible to compress ResNet 101 to retain its accuracy but achieve similar FPS performance as ResNet 18? And finally, many applications can be made with the proposed system. A dynamic system could be created that automatically chooses the best model to retain a balance of accuracy and FPS. A system could be made to alert someone if they have been detected to not wear a mask, or a simple system could be created to not allow anyone into an indoor area unless it has been detected that they are wearing a mask. A usability study could take place to evaluate the effectiveness of the desired application. Overall, I'd be really keen to see someone take this project further, as there's just so much that can be done with it, and I'm really keen to see what people could come up with. And that pretty much concludes this video. I just wanted to end by saying, if you want to know more detail about anything I've spoken about, you can read my dissertation, which I'll link in the description, and also if you have any questions, you could just either comment down below or just send me an email. So yeah, thank you guys for watching, and bye.